When we use those same type of Lewis notations for covalent compounds, you can see that they become quite a bit more complex because we have these shared electrons all around this carbon atom. Remember, the carbon atom has 4, so it needs 4 electrons. That's why you've got 4 chloride atoms around it. Now you can also, instead of having it this complex, you can have only the free the non-bonding pairs shown out here, and those that are bonded, in other words, between 2 different atoms, appear as a single line. So for carbon tetrachloride, it can be either in this form with all straight Lewis structures, or this partial Lewis structure where you've got the non-bonded electrons out here, the non-bonding pairs out here, with these lines representing the bonds formed between this element and these elements here. Likewise for silicon tetrasilane, which is silicon tetrahydride. You can have it either in this form or where you have the single bonds associated here. Ammonia, same way. Here ammonia, remember, it has 5 out there, right? And so it has 3 to share plus a pair. Water has, for oxygen has 6. So here's 1 to share, plus 2 non-bonding pairs. And fluorine has 1 to share, and so it only forms 1 bond with hydrogen. And so that you can see then how from this you get 3 bonds with hydrogen here, and then next place over in your periodic table you get 2 bonds with hydrogen for water and only 1 bond with fluorine. Formaldehyde is an example where you've got a double bond. Here you've got, remember, carbon has to have 8 around it, right? So it has to share 2 pairs here. 2 pairs, or essentially these 2 lines right here. Each line represents 1 pair of electrons. Likewise for ethylene, you got 2 pairs of electrons here. In other words, 2 bonds here. 1 pair here, 1 pair here, 1 pair here, 1 pair here. Okay? So hopefully that's all making sense to you on how you represent all these different types of structures. In this one right here, you've got carbon, and it's got only 4 electrons around it, doesn't it? Here, each carbon has 8 around it. Here, this carbon has 1, 2, 4, 6 here, 2, 4, 6 here, and this nitrogen has a single pair right here, so that it has 8 around it. So this carbon and this nitrogen are neither one satisfied. Neither one of these, all of these carbons are satisfied, but these 2 carbons are not. So what happens here is you have to share 2 non-bonding pairs here, don't you? In order to get 8 electrons around this carbon, and to get 8 around this nitrogen. This is hydrogen cyanide. This one is satisfied. Here, you have to have both of these pairs come into here, and this right here is acetylene. So you have a triple bond here, you've got a triple bond here, a lone pair here, a non-bonding pair here, and a 1 bond here. 1 bond here, a triple bond here, 1 bond here. And of course this one right here, the octet rule is satisfied. So also there's going to be something called bond polarity. It results for the uneven or unequal sharing of electrons. So if you have a strictly covalent bond, for example here, this could be chlorine and chlorine, or hydrogen and hydrogen, oxygen and oxygen, nitrogen and nitrogen. However, if instead you have nitrogen and oxygen, there's going to be some polarity there because of the stronger nucleus that the oxygen has versus the nitrogen. And then ionic is just completely separate. So the meaning of absolute differences in electronegativity is the following. if you have a difference of 1.7 in electronegativity between the two elements, you're going to get an ionic bond. That would be in this case right here. If it's between 0.5 and 1.7, then you've got a polar covalent bond. Anything above 1.7 means you would have a covalent bond like this one. And remember, this is your periodic table electronegativities. And it's in 3D, and I really like this because it shows you the relative values of the electronegativity on this axis. And here what you're doing is it's plotted out the complete periodic table. And you can see fluorine is the highest with 4.0. So 4.0 with oxygen, the difference is only 0.5, right? So likewise here, the difference is 0.5. So all of these are going to be bonded together with each other in terms of a covalent bond. But when you go with some of these and some of these, okay, you are getting much greater differences, and they are going to be ionic, right? 4 minus 1 is going to give you 3. So that means this is going to be a strictly ionic bond. It's well above that 1.7. And so, and you also from aluminum with oxygen, that's going to be greater than, that's going to be a 2. So that's going to be an ionic bond. Okay? So you see how easily that works out. So this is another way of seeing that same thing. If it's 0 electronegativity, or actually it's less than 0.5 in this one. The other example I had was 0.5, 0.4. Anywhere in that range is going to be entirely covalent. The last one showed was 1.7. This says 1.8. Again, just different authors, same concept. This right here goes to the composition of compounds. You've got club soda, pure baking soda, and you've got super washing soda. All these are made up of some form of the sodium carbonate ion. So there are millions of different combinations of these over 90 elements, and some of them we refer to as common names. Baking soda instead of sodium carbonate, washing soda. You have baking powder, by the way, is actually 2 separate molecules. It's sodium bicarbonate and sodium carbonate. And it's difficult to relate these names to the actual molecular structure. For example, quicklime has nothing to do with the little lime on a tree. It has to do with the calcium hydroxide material, calcium chloride, and the way those things are mixed together. The modern approach is to have a systemic set of rules. And it's different for ionic and covalent compounds. One common rule is IDE, means the compound contains only 2 different elements, okay? And that IDE goes on the second of the 2 elements. Now, it's good for you to know exactly what you've got in terms of the old ones, because that's what you're going to see in your supermarket shelves. And so you'll be able to have your own chemistry at home, knowing what those are with respect to the information we're learning now. The ionic compound names are, for example, lithium, sodium, potassium. All of these right here are the positive ion. And so what we're doing is all of these with the positive ion, those go first. It's only the second one, which will be the negative anion, and that forms, if you've got 2 different ones, you have an ick or an for the higher one, us for the lowest. So it's ferric oxide, ferrous oxide. And the modern approach is, instead of trying to do that, is to put a number, a Roman numeral, after the particular ion, indicating what its charge is. So it would be Fe2 for the old ferrous and Fe3 for the old ferric. In the ionic compound formulas, the rules are you write the positive ion first, followed by the negative ion, right? And remember, the charges have to balance. Calcium has 2 plus 2 on it, right? Each chlorine, to form a chloride ion, only has a -1. So each one of these requires 2 of these. So when you make certain that they are equal electronically by this subscript down here. When you're doing your equations and all of that, do not change the subscripts. That changes the ionic species. So calcium chloride is CaCl2. And it is a neutral compound containing 1 calcium ion with a +2 charge and 2 of the chloride ions, each with a -1 charge. Covalent compounds are a little more complex. What they do there is they include, in front of the first portion of that, the prefix, either mono, di, tri, determining the number that you have there. And then you've got the stem name. So monohydride, or dinitro, tetrafluoro, or pentachloro, all of these different ones would have that type of a stem. So the first one element in the formula is named with a number indicated by the Greek prefix. These are the Greek ones, except for mono. Rarely do you see mono. Well, we do have carbon monoxide, but that's to distinguish it from carbon dioxide, CO versus CO2, right? But if it's the first element, rarely do you have a mono there. The stem name for the second element comes next. And again, it's preceded by this prefix, and then "ide" if there's only 2. Okay, here you have covalent compounds of different molecules. Hydrogen usually has just 1 bond. Its valence is 1. Oxygen has a valence of 2, so we can have both a single bond, okay, and a double bond. Nitrogen has 3, so it can form a single, double, and a triple bond. And carbon can form single, double, and triple bonds as well. The formal charge is another concept. In other words, here, and this gives you an idea of the polarity of it, and also gives you an idea of resonance, where you can have 2 different forms of the same one where the electron clouds are sort of dispersed among them. Carbon dioxide has this sort of a sharing structure right here. What you do to get a formal charge is you look at how many electrons are around it, okay? And each bond counts as 1 electron only for formal charge. It's only for formal charge. So this would have 2 electrons here, 2 electrons here, and then 1/2 of each of these, so that would be 2 more here. That would be 6. Now, that is the normal number of electrons around oxygen, so that would have a formal charge of 0. Here you have 1, 2, 3, 4 bonds, so that means that carbon there would have 4 electrons for a formal charge, so it would be 0. And this oxygen would be the same, okay? This structure instead, here you would have 1, 2, 3, 4, 5 for your formal charge on this oxygen. 5 means that it's missing 1 electron from its normal 6. So that would be a +1. This carbon has 1, 2, 3, 4, so it would still be 0. This oxygen, 1, 2, 3, 4, 5, 6, 7. So this would mean that this would have 1 more. That would be a minus formal charge. And if you did it like this sort of a structure, this would be a +2 using that same math. This would have 0, and this right here would have a -2. And the idea is that a structure will always have the lowest formal charge. So this right here is the way in which CO2 should properly be represented. And we'll stop there.